There we go. YouTube finally decided to actually show. The live stream. All right, so we have 2D inverse kinematics. We have some cool stuff that is working. So I guess if I run this, and you know what? I should have fixed the other thing before I ran this. Let me modify this because I turned it off for reasons. So we end up with this demo, which right now is just a bunch of bone segments and stuff, which is cool. All the positions are global. This is the FABRIK algorithm. It's working pretty well. Pretty happy with it overall. The downside of what you can see here is that all of the, none of the rotations are changing. So we're not updating the rotations of any of these joints. So everything's in the right position, but nothing is rotated appropriately. Oh, I guess the other thing is this also works correctly if you have the mouse outside of the detection circle. So it'll still reach towards the mouse in that case, which is pretty cool. Got that all done yesterday. Does it allow for a sort of stiffness of the joint so it doesn't fully fold in on itself? So allow for a stiffness of the joints. You can put constraints on the joints. That is sort of allowed. My understanding is that because FABRIK, which is the algorithm that we were using, is an iterative solve, right? There are multiple steps to getting to the point at which this resolves. That at every step, you can apply a constraint. So if you want stiffness on the joints or something like that, you can apply that constraint after each pass and just correct everything. Supposedly that handles like quite a bit, but I don't have any stiffness or anything like that implemented. I do want to take this to 3D before I do any kind of like constraint generation. You mean more like springiness, you suppose? Like if you move the mouse from the edge to the center, instead of folding backwards, it'll sort of spring out in a partial circle. Yeah, I mean, that would be constraints, right? Like you're saying you want to see something a little bit more like that, but with the mouse like down here. Right? I think that's what you're saying. He moves the mouse from edge to the center instead of folding on itself like this, that there is a constraint on the joint. So for example, the joint that's furthest away right now, so that it can't have an angle of, 5 degrees. I think those are all constraints to my understanding. And those constraints can go in each pass. So I don't think I have the visualization enabled right now. Oops. But if we move this up a bracket, then this shows all of these steps. Which very often is like not actually very many. I feel like it converges really quickly. Oh, you know what? Those aren't being persisted. Anyway, the positions change every time you do the resolution, so it's kind of hard to show. But I don't know. I would try to make this a constant thing so it has to settle between straightened out and what your mouse forces it into. Also that it distributes movements over all bones. I mean, I think you're talking about constraints, right? Also, this isn't like this little demo that we have here. This is not the goal, right? Like this is cool and everything. But it's not what I'm trying to do. Let me get rid of the spawn lots. Let's spawn only a few. What I'm trying to do is transition this into 3D and power some spiders. So this was my debugging for rotations. So really, we're only going to have this. Maybe one more bone. So there isn't going to be a lot of necessity for that kind of springiness constraint that you're talking about. Because really, this is going to be like the spider leg, right? This is the wrong distribution of lengths. The inner one will be shorter and the outer one will be longer, but like, right? Like this kind of idea is really what's going to happen in 3D. You don't know IK terminology. Does constraint do more than you can't be any angle between A and B? I think constraints are a general term. Right. I believe constraint is a general term in this sense. Like constraining a joint to do something or behave in a certain way. Like it doesn't need to be a hard constraint. This is a very interesting topic. You did make it to in Godot GD script. Love it, especially AI systems. Good luck. Thanks. Right now, most of it's working. FABRIK is cool. It's pretty simple to implement, all told. We did it in about 4 hours on stream yesterday. And I had never seen the algorithm before, so that was pretty cool. You're probably thinking about constraints too much in CAD terms. Oh yeah, they're not hard rules, right? They don't have to be hard rules. You thought about making things like IK for spiders and foot IK for FPS rigs, and FABRIK is more limited regarding constraints than other algorithms. Yeah, I mean, I don't need... First of all, this was like a great first project for IK, in my opinion. Worked really well. It was a great suggestion. There are things that I don't like about the way this behaves, necessarily. I think if I... No, it doesn't happen for the positions. Let's see. So let me go back down to get rid of this because I don't want it to interfere. And then I can set this. Run this. So we have the positions, and this is all of the rotations being correct as well. The problem with this, obviously, is the positions are off. But I'm not actually sure they really are. But you can see how when I wiggle this line, that the right thing is rotating, right? And it kind of maintains that rotation. So really what I need to do for this algorithm right now is try to combine the correct positions with the correct rotations. Which I can't figure out how to do. So the algorithm works in global space is the way that we'll start, right? So when we end up with current positions here, current positions ends up being fully global. The way FABRIK works, does it solve constraints in multiple directions, as if every bone has a spring back to angle 0 with a force of 1 constraint? Does it actually even out in the end? Like maybe it only propagates stuff. The name of the algorithm is forward and backward. FABRIK, forward and backward inverse kinematics. So that probably answers your question, honestly. Overall, the algorithm, let's see if there's a visualization in the slideshow over here. Overall, the algorithm, if you have this chain of like 4 elements here and a target T here, I can full screen this. So you have this chain of 4 and you have a desired target. We want to put P4 on target. And the way to do that is starting at P4, we move P4 to target. Then we move P3 into that vector using the bone length, then P2, then P1. And then we do the exact same thing using P1 because P1 just moved off the root. We move it back onto the root, and then we do the same thing in the opposite direction. And we do that n number of times until P4 and T have like some margin of error, right? We have to decide it stops at some point. So during this process, you go backwards and forwards, or forwards and backwards, sorry. I renamed my stuff to match the paper. If you go forwards from P4 to P1 and backwards from P1 to P4, you can do the constraints, I believe, at any point in that process, as long as everything converges. And then you get a bunch of iterations out of it, which should also converge. As long as the springiness isn't done at the wrong time so it can converge. Yeah. Yeah, I mean, if you made something that was like super springy and never really converged inside of a reasonable amount of time, which you could totally do, right? You could make it like infinitely springy and they would just like bounce all over the place. For that, we also actually, for other cases, have to bail out early. So for this whole loop, we're doing a max iteration count. In the base case, we never hit this iteration count. It never hits 10. But in the case of, I made something wrong here. Let me leave my positions. So in the base case, I left the rotations in too. Damn. Hang on, I need to take the rotations out because the rotations are broken. Well, the combination is broken is really what it is. So in this case, where the mouse is somewhere a bone can't reach, this will trigger the max iterations. So in this case, we have like a long bone reaching out and a short bone reaching back, and the mouse is somewhere in the gap between them at the end, which means that we do hit that max iteration of 10. So we do have to have that bailout condition regardless, because there are situations where it happens. You meant more like you need to apply the springiness so it's not applied after a solve loop, but before being checked. Right. This is a whole iterative solve, right? So it is do the forward and backward, apply constraint, do forward, backward, apply constraint. And every time you loop back to the top, you do the diff check effectively. Hey, are you planning on supporting more effectors in a single hierarchy like they have in the later slides? I don't know. I don't really know of a use case for this right now. I saw some people using it for like tethered ropes or like tethered I don't know, like a rope with a split that connected to something else, like balloons or something. There's no explanation for this part in the slides. So I was reading the paper a little bit. They have a whole section on it in the actual paper. But I don't know. I don't know that I don't know if I will. If you want something more, you'd be really interested in that too. If you want multiple end effectors and more complex constraints, then you likely want to look at Zalo inverse kinematics. Zalo inverse kinematics, this one. Quaternion cyclic coordinate descent, or CCDIK. Yeah, this is a whole field, so we could do a whole bunch of different examples and stuff. I do want to take this into 3D before moving on to a different approach. But I'll bookmark this for later. Also, you say multiple end effectors. Suppose not for spiders. For spiders, they're all going to be separate legs, so it's not going to be, as far as I'm aware, multiple end effectors. Also, multiple end effectors would be like ropes that split into two. So I need to find a use case for it. Right? Like if I'm going to IK a character's legs, that's going to be a small set of joints, right? It's going to be like just the thigh and the shin or something like that. With like either a fixed or a, adjusted foot. It's not going to be the whole armature, right? I'm not going to IK the whole armature. I don't really, like, you could theoretically do a full IK, but I think that the physics games like that are just not super interesting to me. So I don't know if I'll do it. But for spiders, you want the elbow part to be pointing upward. You currently have no way to do that without constraints. Right. I know. I'm aware. That's why we were talking about constraints earlier. Also, let's see. Tunic spiders. The freaking spiders. Oh, this is actual spiders. I wish I could search for just the game. Sorry for anybody who is arachnophobic or anything. You would assume upper body. Arms and head are 3 end effectors, so when a handle reaches further out, the whole upper body and other arm couldn't reach another direction. Yeah, I've seen a couple of IK spiders in Minecraft during my searching. This is Reddit. Can I do this without the sound and hopefully they run directly into the spiders that I can see? Come on. I know roughly where the spiders are. I just need to find their... This is roughly spiders. Oh, they're speed running it? Okay. Do I have that on? No. I just want to see the spiders. I don't think they ever see the spiders in this video. Well, you don't really understand the YouTube XP thingy. I don't know what the YouTube XP thingy is. Ambush. There's one that I know that is. Let's see. This one. This shows the spiders. Is why we're watching it. So these are like very simple, right? They're not really even, if you look at the legs, they're not even really lerping. Right? They just kind of warp forward almost. So they're using like target positions on the ground as far as I can tell and just warping to that target position more or less. In any case. Oh, your messages have a number 2 after them, but you don't understand how you achieve that. If it was by messages, wouldn't it be number 1? So it can't be that, but then what is it? Yeah, I don't know. I don't actually know. Maybe if I hover it, it could tell me. I didn't realize y'all could see that too. I don't even know what this is. Oh, you and 4X have 75 XP, whatever that means. So I think y'all have sent, let's see, question mark. What does this say? A place for fans to stand out in the community. It resets every stream, so this is just this stream. You send live chat messages or super chats and super stickers. Please don't do that just to get a badge. I don't know. I have no idea. Because if it was number of messages, then you've sent more. So I really have no idea. Maybe the description is inaccurate. Okay, so we could also cover the current code as it stands. It's so strange. How does it figure we have the same XP? Do you write too much and it thinks you're spamming to get rank? I don't know. I don't know if there's a timeout or something. I've literally never once read any documentation about that. I don't do a lot of the stuff like that. I think the only thing I have enabled on the channel is like super comments can happen. Silent ping. So yeah, anyway, the algorithm here, we spawn a couple of bones. Right now I have a couple of meshes on these. So if I run this, you can see the meshes. One of the issues, so we kind of assumed that there was no other like children of bones or anything. We kind of just like go down through the bones. I don't think that works in the long term. But for now, we're just assuming that child of is the correct relationship to use, which is why when you put mesh 2Ds on these, they stick on the joints instead of being like offset. Because I think the only way we can offset them, we could offset the mesh positions itself, but I don't really want to do that. I want to make it a child and put it in the right position. So that's this spawning. So we've got inverse kinematics component at the root position. We've got this bone length component, which is also important. Then we've got a couple of mesh materials, another joint, another bone length, and then a final joint without a bone length. You think it would be smart to abstract the IK stuff into a more general representation, not Bevy components, and simply read components to transform to abstraction, solve, adjust components. That's what we're doing. So FABRIK is inherently meant to work with global coordinates. Yes, we get global coordinates out of the end. The components here are just the root node, really. Right, I've got bone length here, which is just kind of a helper component that I'm not sure we actually need. But these are just for querying. They're not for storing the state or the logic or anything. So if we go down to the actual thing that's running, right? This update system does everything for our IK. So we use inverse kinematics to query for bone lengths for the roots. And we have a bone length query, but that's it. We just, like, once we get this data and once we get the transform data, so the first thing we do is if we don't have a mouse position, we can't actually reach anything because there's no target. So we bail. Then we start our for loop. So this iterates over every IK body in the scene. And we label that with IK body so we can do a continue for this loop if anything goes wrong instead of return or break. Why wouldn't the math also work with the local coordinates by always assuming the parent bone is at 0, 0? That would still only be local to the root bone. So you would still be like in root bone space. So I'm not sure what that buys us really. I guess some simplicity, right? Treat the root bone as 0, 0 and then move everything off of it. But we have easy access to the global positions. And we have to do that math either way, right? Like we have to do the math of subtracting those vectors either way. And what we don't have available to query is relative to root bone transforms, right? There's no root bone space that we can query. We would have to calculate that. You didn't mean root bone space, but each bone sees its respective parent as 0, 0. I guess which one is the parent in that case? Because the algorithm goes forwards and backwards, so it traverses up and down. So which one are you thinking of as the parent? I guess if we treat the root bone as the parent, then we have to move the end effector to the target, and we have to move the root bone to the root position. So the root bone can always move back to 0, 0, I guess, technically. But then we have to kind of like keep that data around. And then I feel like it just gets a little bit weird. Trying to think through it in my head right now. I think the paper assumes global space. but I'm not sure that that's like a hard requirement per se. Right, they never say anything about spaces. Yeah, they never say the words world space or any other space. They never mention world anywhere in here. So theoretically it doesn't matter, I guess. You could do it anywhere. They do talk a little bit about constraints. You mean more like, does it matter for the algorithm if you assume a different coordinate space each step? Like bone 1 to bone 2 has bone 1 at 0. Hang on, there's somebody knocking at my door. I'm going to be right back. All right, we back. Inside the individual solving step, I'm not sure what changing the spaces buys us. Is kind of what I'm at right now. Like we can look at the code and I'll show you what it does. And then you can tell me, maybe. So we got every IK body root. We grab the total length of all the bones. That's what the circle on screen is when it shows up. That's how far we can possibly reach. If the target isn't reachable, we return. Otherwise, we get into our actual behavior here. So this is kind of the bailout section. If the mouse is outside of the circle, then basically all we do is line up the bones and set them in a line towards the mouse. And then we continue with the loop to do the next body. If we're supposed to keep processing, then we construct all the current positions. These come from their global transforms. So we have all the global positions in a vec. We get the end effector, which is the last bone in the chain. And then we calculate how far the end effector is from the target position. If the target position is close enough, then we're done. If we have exceeded the number of max iterations, then we're done. And this becomes the loop for the solving step, effectively. So this is the forward pass, this and the little code below it. We grab the last position and push it onto the target. And then we iterate over all the other positions, doing some math and projecting that vector using the bone length onto... See if there's a visual that I can use in the paper. This piece of the code is doing this part. So we project, we've moved P4 over. That's this code right here. We move P4 onto the root. And then we have to take P3, get the vector between them, and move P3 based on its bone length along that vector from P4. So I guess what you're saying is we could potentially treat P4 in this scenario as 0, 0. And then calculate the position offset from that. And then treat P3 as 0, 0 and calculate the position offset from that. But the math that we're doing is kind of already handling that. Right, our vector is the difference between these two. And then we project along that line. Does that make sense? Or because like I'm presuming you would want 0, 0 for the like first bone, and I guess that's just not a useful measurement in any other way. Right? Because P1 is our root. P1 is the static bone at the root. That's not supposed to move. And P4 is moving to the target, right? So if we treat this as, I guess, P4's local space, then we have to translate into and out of that space. And that doesn't seem useful. Unless I'm missing something. Is there some reason that you think that is like a useful thing to do? In any case, this is the forward pass. So we move it onto the target, and then we iterate, moving each vector into its spot. So we end up with this visualization on the right here where everything has moved into its requisite spot, which pulls the root off of the root most of the time. So since we pulled the root off of the root, we have to do what's called a backward pass and go from root to tip. We do the same thing. We move the root onto the root position there, which I think is shown in the next diagram. Yeah. So we move the root P1 onto that root position, and then we move all of them in the same direction. We do the same, effectively the same calculation with slightly different orientation. And then we set the diff based on where P4 ends up. So P4 ends up somewhere. How far is that from the mouse target is this diff. And then this loops again. If the diff is greater than the tolerance, we're done. If not, we do another loop. So we do as many backward and forward passes as we need. or forward and backward passes, until the tip at the end of the backward pass ends up close enough to the target. For now, what I'm doing is once we do all of that calculation, we're doing a gizmo. So this gizmo, the pink gizmo that you see here, is the final global positions of everything. So you can see that we have, like that's working. You guessed that'd be P3, that's 0, 0, and P3 has moved from 0, 0. So the next step is P2 to 0, 0, but P3 is now further and P2 has to be moved towards it. Like it's actually not a big change, you think? But what does it do for us? You're saying treat P3 as, so you're saying treat the thing that we were supposed to be moving as 0, 0, right? So what does that do for us? Like, why is that useful? Because remember, the other thing is that this section has to run for every iteration. So the more it would allow you to rely fully on transform instead of global transform, only if P1 is always 0, P2 is always 0 for P3. It's only one direction. The thing you're moving in 0, 0 is one path in one pass because that's the nature of the transform hierarchy. The other pass would be swapped. Right. So you end up with local space coordinates for this P. But let's finish covering the algorithm because there's a reason that this is like not super useful. So we draw the line for the algorithm or for the final positions, right? That's this pink dotted line here, which is great. So everything's moved into position. Then we have to iterate over everything and set all the transforms. In this case, we get the relative vector, and we use the relative vector to set the transform. The end. So the reason that using the local transform space is not super useful is because it requires more work in the iterations, and then we're removing what, like a vector subtraction from later. So we're replacing one vector subtraction per node with n space transformations in the algorithm. The other thing is that the rotations are not taken into account by the algorithm. So the point of the algorithm is that everything is straight lines, and we're basically just projecting vectors on straight lines, which makes it super easy, super simple, and super fast. Once we have to start doing dealing with angles and like matrix multiplications and stuff, I think the other algorithms end up. Right, and that last step, getting the relative vector, is what this would save because you'd already be working with them, and I don't think it'd be more work. It's a hard-coded 0, 0 per pass. So this is from root to tip. So this is the easier of the two. So you're saying that P1 should always be 0. So we should never work with this. So the P2 vector is from 0, 0 to P2, but P2 is going to be in its own relative space. I guess you're saying that P2 would always be relative to P1. So we remove this subtraction here because P2 is just P2. And then I guess we don't need to do P1 minus, right? So it's just vector normalized P1 bone equals P2. So this pass is fine. That would technically work. And then we end up with, how do we do the math for the next one then? Because if we're always treating P1 as 0, then we get to P2, and P2 is then automatically treated as 0, 0. But what does that mean for the offset of the other vertice? You think it's easier in the other pass. Okay, let's look at the other pass then. Here's the other pass. This is going quote unquote forwards, which is actually from 4 to 3 to 2 to 1. Right. So the first step here is that we have to pick a position for P4. So how do we pick a position for P4 if P4 is always 0, 0? That's what I was mentioning, I think right as you came in, Xavier. Basically, like, the algorithm is based on straight lines. So we have to do the rotation calculation afterwards anyway. And having everything in relative space doesn't really help that calculation. P3 would need to subtract the previous calculated P2 offset, you think? Well, no, let's just start with P4. So we're at P4, and you're saying set P4 to what? We have the mouse position, which is the target, right? So what is P4? We have to move we have to move P4 to the mouse position as the start of this algorithm. So how do we start if everything is local space? Right. If it's relative, it has to be relative to something. So we would have to use the same logic here. We would have to set this to a global position, which ends up meaning that P4 and P1 both have to be global, and then everything can be relative to that global, but only for one pass in one direction. Or we can kind of like backwards orient ourselves. If we are doing the full iteration, so let's say we set P4 to that global position, and then we treat P2 as 0, 0, or I guess you want to treat P1 as 0, 0, right? So we have 0, 0, and we have the mouse position, which is global. Right. So we have to end up doing like more space transformations to get things into local space, which means that we already have to know where they are in the first place to be able to transform them into the local space. And I think we have to do that every pass. Also, just to point out, every other implementation that I've looked at all works in global space. Everybody uses global space. So if there was a reason to use local, I haven't seen it. That all said, once we get down here, we have the global positions, which we can easily calculate the relative transforms from. So this all works, right? All these positions are correct. And if we do quaternion inverse as we iterate, we can get all of the rotations to be correct, right? But I don't know how to combine them. If we combine these, it gets really unstable and is not working correctly. And I think that's because the transform or the translation location has to be it does look cool though. Working with quaternions, yay. So if this iteration is basically, we have the root entity that we're basing on, and we have the next entity. And here we're setting the rotation of the root and the transform of the next. And the transform of the next for a rotated root needs to be something. Needs to be like rotated around that point or something. And I don't know what the calculation is supposed to be. You mean fair enough, maybe it's just pointless, but it seems surprisingly doable. The code is on GitHub if you want to try it. I would be curious to see if you did it. Your suspicion is that if written out, you could end up simplifying the math bit because of the inline of the coordinate space transform, but since it's a tighter loop, it's probably not enough. If you can simplify the math, I would be very interested in that. I think that the math currently in one space is pretty simple. The only things that we have going on are subtractions and multiplications. So for each iteration, we do like 2 subtractions and a multiply. Getting much simpler than that feels tough, but maybe you can do it. And then calculating the relative transforms is just the global minus local. Because right now you're doing global, solve, local, and then Bevy does global again. Well, yeah, I mean, it would be nice to just set the global, but we can't do that as far as I'm aware. Right? That's not a problem with the algorithm. That's the inability to mutate the global transform. Right? If we could mutate the global transform directly, then we can place everything without doing any additional calculations. We would have to propagate back to the transform, I guess, or ignore the transform entirely, but an easy way to do the calculation: calculate the position and rotation in global space, use the transform of the previous bone to transform into local space. And you suspect if you ever introduce transform scale, you'll end up with all sorts of weirdness. Why would I introduce transform scale? An easy way to do the calculation: calculate the position and rotation in global space. Use the transform of the previous bone to transform into local space. Calculate the position and rotation in global space. We have the position, right? And we have the angle, the rotation, right? This is global angle and the vector from the last root to, so we have all the global positions and we can get the angles, right? The question is, once I do this rotation, this transform has to be transformed into something that works with this rotation. And I'm not doing that correctly. Sometimes animators scale the bones. I'm imagining a more general application of this than you are, where you try to use it for GLTF meshes and such, which you assume use local scale sometimes, but you haven't ever paid attention to that. I mean, right now, we're just doing 2D. We are moving into 3D after we solve the rotation issue. I think you're just you're trying to jump ahead into 3D and GLTF before we actually get there at the moment. Let's say the root bone local space is the same in world space, so that one does not need transformation. For the following ones, calculate the global transform and divide it by the inverse of the parent transform. You can invert the parent transform? Hang on. God, I hate sidebars that expand. This might require going from transform to matrix and back to transform. We can do that. We can get the matrix. You always want to transform a point in local space to world space, or if you need the inverse transformation, see global transform point. See, the problem is I don't think we have access to from XYZ. Because I was looking at this trying to get it to... Maybe this does work. Maybe I was just really tired and missing something. Okay, well, that probably makes it significantly easier, honestly. Yeah, I'm not really looking for optimization at the moment. So we have a global position. Transforms a given point from local space to global space. So you compute transform. Down forward, mold transform. Reparented to is interesting in this context. I feel like it's a little bit weird. Reparented to doesn't access anything from systems or anything, so it could be useful. So returns the transformation self would have if it was a child of an entity with the parent global transform. So theoretically, if we can construct a global transform, right, then we can pass in the parent global transform. We can do the reparented to, or we can do the math ourselves. By the way, you can directly update global transform. It's easy. Don't use children, child of, and use the transform. I'm assuming you mean don't use the transform? Oh, you mean unparent everything and then use transform. That's not updating the global transform. That is having a non-hierarchy, right? You're still updating transform, which then updates global transform at the end of the frame. That is like an option for this demo, but it's not an option for moving forward. So reparented to parent affine inverse. So we are inverting the parent affine times ourself, and then dealing with scale, rotation, and translation correctly. This seems like what we should be doing. I don't think we have actual transforms yet, so I think what I'm going to do just for clarity is build the global transforms. All right, this is XY, XY, so we can get back to this if I just map over it. No, you're saying that's the intended way to work in global coordinate space. Don't use the hierarchy for your meshes. The issue is that you can't update global transform in Bevy. It's that you can't mix. Yes, but everybody uses the hierarchy. Right, you can't have hierarchy, but also update global transform because there's no way to opt out of the propagation. Right. To opt out of the propagation, you have to restructure your application and the way that you're spawning things, which is fine. It works. Yes, but we can't avoid the hierarchy in this situation, especially if we're considering moving to 3D and moving to GLTF. We can't avoid the hierarchy. So we have to fix this, is really what is in my head. So current positions. Right now, we unfortunately have to do this, which makes it look a little bit messier than it actually is. But this is basically saying we have the root entity and all of its descendants as one iterator. And then we zip that with the current positions. And we're tuple windowsing over that, which may not be correct in the end because we don't actually end up touching the very last item. But that's okay. Okay for now, anyway. We could also do peekable here. That's one of the things that I changed up here. So for the code up here, we get that current positions vec. We turn it into a peekable mutable iterator. We do a while loop over that with the previous and the next, and then that gives us access to do everything. So we could take the same kind of approach down here, but yeah. You went from 3 to 1 just now. I don't know why. Right, you understand that, but you said it as if Bevy didn't give you the option. It does. You just have other constraints that don't allow you to use the intended way to opt out. Right. But what I mean is you cannot, how do I frame this? You can't make a particular node opt out. You have to restructure the hierarchy to work with global transforms, which is totally valid, but you can't opt out for a particular node, right? Like there's no way to put a component on something and be like, this is a global entity. So I see what you're saying and how it could have been ambiguous, but I did mean specifically that there was no like component you could put on. There was no choice you could make to opt out. How would opting out for a particular node work? Why would it make sense for it to still be part of the hierarchy? I mean, we have generic relationships. I get what you're saying. Like you're kind of trying to imply that if you use children and child of, that relationship is meant to work a certain way, and if you don't want to use that, then don't use that relationship, which is totally valid. I'm not saying there has to be another solution. I'm just saying you can't. We're going to into iter this. We are going to map over it. And I'm going to turn all of these, I think, into global transforms. Position.x, position.y, 0. So we'll have global transforms and bone length. That's essentially what you're saying, especially now that we have custom relationships. The correct solution for opting out is to use your own relationship for that. In the abstract, I agree with you. In the context of knowing what people are going to try to use an IK implementation for and how they're going to use it, especially as we move into GLTF, you have to use children and child of for this armature. There is no other option currently. Right? So this could be like a bug in the way that armatures are handled, right? You could claim that this is a bug in the way armatures are handled for sure. You could have like a bone of parent, right? And we could be traversing bone of, which is totally valid. And I don't disagree with you. I'm just saying that's not the way it works right now. And to make it work like that, you would have to make everybody opt into using a new special relationship in a context in which they don't have access to like the nodes. You'd say it's a leftover from Bevy not having custom relationships, to be honest. Yeah, I would agree with that. Also, the animation stuff existing before that. Your mistake. When you said divide by the inverse, you meant multiply by the inverse, which is kind of the same thing as dividing by not the inverse. Yeah, this is what you meant, right? Exactly what's happening here. Take the inverse, multiply, and then deal with the scale and rotation. This is what I'm trying to accomplish. I'm going to take I am assuming that when I do this, this is going to give me a position that is relative to the parent with the correct rotation applied. That's what I'm thinking. If it doesn't work, it doesn't work, but that's what I'm thinking. So these two are then global positions, and the relative vector here, I don't even know that we need the relative vector anymore if we're going to do it this way. I think we do. I think we need to set the angle ourselves. Because we currently, I don't think we currently have a concept of that rotation existing. And this reparented to is not going to know we want one to point at the other. That's my thought right now. If we do a rotation, where do we put the rotation in this context? If we have a global transform and a global transform, we can set up the angles ahead of time, which I think is just the angle that we have. And then we can parent it, and hopefully the angles are taken care of for us. So we do need these relatives. Right, relative is xy, xy. Then we get the angle. The angle is an F32 here. We turn that into a quaternion. Comment this stuff out. Hey, Chris, probably a common question, and if so, sorry, but favorite resource for learning 3D math? You've been going through a 3D math primer for graphics and game development, and it's great so far. I would, what kind of 3D math? I guess if you're looking for linear algebra, also just a general suggestion, 3 blue, 1 brown is great. I really just misspelled their name and put a 2 instead of a 3. They have a whole series of videos here on 3D transformations, how to intuit like what a dot product is, etc. Freya's math for game devs. Right, this one. Freya also has a 3-part shader set of videos that are pretty good. They're kind of long, they're a little bit live streamy, but they have good information if you could pay attention. Those are my suggestions. Okay, so don't need that transform. This is going to be the current rotation, right? So I guess I want to set the rotation of the root, which is awkward. I feel like this should be a pass before we do everything. Not sure how to do it with global transform, but with normal transform, you can just construct it with the rotation and convert to a matrix using 2 matrix. I don't think I need the matrix. This is a function on global transform where we can reparent one global transform to another, or at least give us the resulting transform of being in the place where that other global transform would be. So it's the offset from that other transform, global transform, sorry. I think this does what we want. Unless you're saying it doesn't. Yeah, non-origin preserving transformation. Every linear transformation is affine, but not every affine transformation is linear. It does what we want, but it does so by passing a matrix. Yes, but we would have had to get the matrix anyway, right? One of the things that I'm interested in here is if there is a function in the Bevy prelude or in the Bevy set of functions that we can use, I think that using it produces better educational material in general. So if this is going to be an example, rather than having a lot of little scattered math bits, if we can have global transformation reparented to, then that helps people understand IK rather than, yes, but constructing something that can give us that matrix is easier IMO using transform than global transform. Why is it easier? They both have from XYZ and the scale, right? And the rotation. Or can we not do a rotation here? The thing that really tripped me up is that from XYZ isn't even in here. Like, it's in all these examples, but it's not in the documentation, which is really bizarre. It must be hidden in the docs, which, I mean, like, I kind of get, because I don't know. Yeah, doc hidden. From translation, from rotation. I mean, I get it on some level, but on the other level, it's like, I really wanted to work with these functions. Oh, another video rec for 3D math. Every 3D concept explained by Digitalist is quite decent as a primer. That's not one that I've seen. Is there with translation? I don't think the with functions exist on global transform. Which just generally kind of feels weird. Like, if I have global coordinates, there's no way for me to construct a global coordinate and then translate it into a local using Bevy's APIs at the moment. Does that feel accurate right now? I guess theoretically, if we have a transform, we can construct it in the way that we want with the rotation and the translation. And then we get the affine here, which will turn it back to TRS for us. And then this multiplication is all we need to do. So we actually don't want this. Because we don't need it. It makes sense to me that the global transform is harder to directly update as well. Bevy thinks you should update the transform of a non-child if you want it to work in global coordinates. Yeah, I mean, yes. It's, how should I frame this? I think that that thing should probably not be called global transform in that sense, if the goal is that you can use transform as a global transform, right? Like, if we're not supposed to use global transform as global transform in logic, then it should be like computed transform. And we should have a separate, like, transform should just exist without a global transform existing. And there should be a note in the docs. Yeah, computer transform. That's literally what I just said. That's funny. Yeah, that sounds right to me. Same brain cell. I'm glad that you passed it back for a second before I let it go again. Okay, so we have the angle that we need. We have the relative vector. So we need the global. We don't need relative right now. Relative is just for calculating angle. So then we need transform from XYZ. We'll let parent transform from XYZ. Previous no global position dot X. I named this super nice for 0. So we've got parent is this with rotation angle quat. We need the quat from axis angle. Axis being what? Dir or vec? Vec. Vec 3, z angle being angle. So that should be the right parent then, right? So parent with the angle of the relative vector between the two. And then interesting as to why this is not available. Tell me this is going to be like a private function or something that I tried to use. Compute affine. Right. I guess we can get the matrix anyway, but you want to do 2 matrix? You want to do matrix times transform instead of because if we do this, then we can do 2 scale rotation translation, which is just a nice function to have. I feel like using words for this feels better than using direct math, right? Current node is going to be transform from XYZ. What's the current position? Global position. Excuse my naming here. I've been kind of juggling different approaches to trying to do this. Right? So this ends up being vec3 quat 3, which we can then do, we can just set because we have mutable access to this at the moment. Right, so here's our actual transform, the one we actually need to update for real. And then transform dot rotation. This is vec3 quat vec3 scale rotation translation. Let's do them in the same order. Transform dot translation. And pray it works. So the rotation is inverted. Or actually, the rotation is correct, I think. I think our order of operations is incorrect. The calculations we are now doing include the root entity, but only set transform for the current. And we're doing Windows. So we never set the rotation for the root entity, is what I'm thinking at the moment. The fact that iter descendants doesn't work on itself is awkward. So what we need is, let's see, angle. Angle still needs to be used to set the angle of the parent, because the parent angle isn't getting set. The current one is, so we really only need to do this again for the root, which is awkward because it's yet another situation in which we kind of need to like pop out to doing one pass for the let's do the update root node rotation. Relative would be current positions 0 and current positions, no, current positions 1 and current position 0. Don't use this with less than 2 bones or it will panic. Then we get the angle, current rotation. This is all we need, right? We only need the current rotation. And then we have what? Transform dot rotation equals. And we have root entity just sitting around ready to go. So this should give us the rotation for the root unless I messed something up. Let's see. Bone length. What is it? 1.0. I should really make a struct for that. Anytime I end up getting into like 2 indexes next to each other, I start to be like, oh, this should be anything else. Okay, so we're pretty good here in general. This then is at least stable, which is more than I can say for other attempts. I feel like we're not setting the rotation on any of the roots. So I think that this needs to come back into actually the loop. Because the parent needs to get that rotation set. Right? We've done all these, and then we have to make sure to set the parent rotation. feels weird. So this is inverted, but it is doing the right thing. The other problem is it spins in rotation as we spin. So there is what, some kind of issue here. It's not counteracting, it is. Wait, did I not invert this? No, I did invert this. Compute affine inverse, compute affine, do scale rotation. We set the rotation. It would be the same. Your guess is the parent rotation is already set, but we still use the one cache previous to that. Parent rotation is already set. Parent rotation. So we have this array of global positions is what we have. And the parent rotation, the new one, will only be set after the first time we do a pass. The transforms that we're calculating here are new transforms. So they are transform for the parent, let's say, go through this code one by one, line by line. We have an iterator over the root entity and the current entity. So we have all of the global positions in a vec, and we're iterating over them in Windows. We start with root and first node, P1. I guess P1, P2, according to the paper. We get the relative vector from the next position, or to the next position, we should say, which we turn into an angle and build a quaternion from. Right? So we have the angle from root to next node. We build the parent transform from the parent's current position. So it's the computed from the algorithm current position and the new rotation that we just calculated. So this parent is what the parent should be, but is not currently because we haven't applied it yet. In the loop, get the parent rotation from its transform, set the previous pass, and not the cached global position. What do you mean by the cached global position? What do you mean by the cached global position, though? There is no... this global position is not the global transform component on the entity. We have our own full set of data here. Oh, you think root entity, children entity, and zip with it. Yeah. It is current positions. I guess this is named poorly, is really what it is. This is the index 0 in current positions, is what this is. Right? It's not doing a lookup in the component for the global transform on the entity. This is index 0 in current positions. right? And to show you current positions, here's current positions, the original definition, which is a vec, where we go through and we grab the global transforms and we get the XY and the bone lengths. And then this is the data we operate on for all of the passes. So this updates and then mutates into the expected final data. Right? So when we go to, this is all the mutation. When we go to current positions here, this previous no global position is the computed global position from the algorithm. It is not cached from a previous loop. I'm doing a lot of destructuring here, but yeah, it's a little messy. So global position and previous no global position are the algorithm calculated positions. Okay, anyway, the parent transform should be the one we calculated in the previous iteration of the loop. Which loop? And the parent's transform needs to be accumulated. The parent's transform needs to be accumulated? Parent's transform needs to be accumulated. I guess the... Which loop? This loop? So... given any particular position here, if I can hold it steady and just go up and down, you can see that this is actually accurately rotating. But it's 90 degrees in the wrong direction in this particular position. To get the local transform from a global transform, you need the global transform of the parent, not the local one. Yes. Yeah, I mean, we are using the global ones. Okay, but that means we're already using the global positions, right? So we don't need to accumulate anything in the loop if what you're saying is that we need to use the global transforms, because we have the global transforms. But the angle, is relative based on the global. The angle is clearly not the, well, the way I'll frame it is the program is clearly behaving wrong when it comes to angles. So there is something that needs to happen here. I will say the base rotation, the middle, is the correct angle. So we're doing the correct calculation in the first loop. What we're not doing is the correct calculation in the second loop. I think we only get 2 loops here because we have 3 joints and we're windowsing 2 over them. So I think we only get 2 opportunities for this data to be wrong. And it's correct in the first one and wrong in the second. So if I don't set this rotation here, then what we end up with is the same issue for the child, right? Effectively the same issue. And the root is not rotating at all. So I think we have to set the parent's rotation here, at least for the root, so that we can get the rotation of the root as expected. Now, the issue here is that the local rotation is correct in the sense that the rotation of the parent is impacting this in addition to the rotation of the second vector. What about handling the root outside? I think it's the same thing. We just did that, but so I can just uncomment it. Let's pull this. I think that's everything. Relative angle, current rotation, set the rotation. So this sets on the transform of the parent. This is the actual transform that it's set on. When we do that, the rotation works. And then the rotation for the for the last node is the only one that seems to be working, but is so the second node is wrong currently. And the third node is behaving appropriately, I think. So there's a calculation for the angle that is wrong somewhere. Let's get rid of that. So we're using global positions. We're getting the relative angle between those global positions. We're getting the angle between those global positions. We are calculating a parent transform. Although in this case, we don't technically need to. We could just get it. Well, that's not true. It's kind of true. I only want to set things when we're done with them, is really my thought process here. So this is a constructed transform that represents where the parent is going to be, which is the same thing we set it to earlier. Then we get the current node, which has no rotation, right? Which I guess technically this has a rotation, so we would need to potentially window over 3 elements here, which is really strange. That feels weird. That feels like I'm going in the wrong direction. Then this is our kind of like test. I should name this something else. This is going to be, I don't know. Do we maybe even not name this and just stick it here in a parenthesis? Right. So we aren't applying a rotation to the current node. So we either have to do that here or we have to do that in the previous iteration of the loop, right? If we do it here, then we have to get the next node to get the relative of the next angle. right? We have to get this vector. This relative is probably the wrong name for that, but we have to do this calculation again for the next node position. So we end up with what I think is the rotation never getting set for successive nodes, right? Which is why I tried to move it into the loop before. You're a bit confused by this angle. What are you confused about this angle? This is global position, vector difference as an angle. Why do we need the rotation difference? I don't want the difference. Well, okay. Let me explain why I don't want the difference. I don't want the difference because I don't want to call functions that are like dot rotate. So I want to be setting like the fully done value. I don't want to be calling dot rotate on every iteration. The difference compared to the initial rotation. The difference compared to the initial rotation. Right. I think if we can get the difference, this is why I was hoping to use the affines to do this, because if we think about the angles, we have to think about, if we're just handling rotations and you think about it super naively, you end up with the root being rotated in some way, the node that is rotating around the root being rotated by that rotation in some way, which then needs to get added to the actual rotation or the diff between that rotation and where we need to be. Needs to be set. I guess that's the diff you're talking about. In the start case before the IK, the bones already have a local rotation. I don't think that matters. Later, Lund. Enjoy dinner. In the start case, basically the start case is just to have values. The start case values all get thrown away. Right? We don't care about the start values. They're all getting thrown away, all of them. We reset all of the transforms every time this runs. Because the whole algorithm is move everything. So we take all the transform components at a high level. We turn those into a vec of global positions. Not the component, just the values, a global position value for every node. We apply the algorithm forward, backward pass up to 10 times, and we end up with the global positions for every bone that is supposed to exist. Now we need to take those global positions. So we have a list of global positions, right? X, Y global positions. We need to take that list and turn it into a hierarchy of transforms. That's the problem being done here at the end. So if we Windows over that list, we can get the angle between the two nodes. And that is correct for the global rotation. I think that's correct for the global rotation in all cases, right? So if we are putting things in the right places, those should be the right angles to use. And thus we don't need to care about the diff. Now, the thing that I'm not sure about is the rotation of a root node can apply a slight rotation to a child, in which case the angle has something is wrong in that angle, right? I forget which version of the code we're in right now, but I'm going to run it. And we're going to look at the actual. So in the current version of the code, we are setting the root rotation before the loop. We never set the second node's rotation. And the third node rotation is sitting basically at the forward position. So X is forward in Bevy's 2D. So it's basically sitting at the forward position, bone length away from the second node position. So really all this is that these are rotated, right? Because if I line this up correctly, then it's correct. So the only thing we need to fix here is the rotation of the second node. The distances are all correct. So the question is, for that second node, what do we do? And that is where it comes into, should it be part of current node? I don't think so. But we are setting it here. But in real common use armatures, the bones do not always have the x-axis pointing to the next bone. Right, but I guess what do you mean by that? Because the armatures used for IK have to have some kind of concept of forward, right? If you don't have some concept of forward, as far as I can tell, then you don't get the effect of all of these snakes and everything that people are building, right? Oh, you're saying the start angle needs to be taken into account because you think that it should be maintained as an offset? Like we should calculate the angle of the original and then try to maintain that over the entire length of the algorithm. So in that case, we would need to store that as component data alongside the bone length. I don't think that's our current problem, just to be clear. But what you want here is bone length, wherever I've defined it. And you want something similar like bone angle. Bone angle initial, right? Like when this thing loads in, there's an angle between two bones. And you think we should take that into account for where this thing exists in the real world. Which I think is fine, but I also don't think is our current problem. Right? I think that's a different problem. Unless you think that that is the entire problem here. But none of our positions are in the wrong spot. It should already be stored in the component because the skinning code needs those. We don't have a skin yet. We don't have a GLTF mesh. We don't have any of that complexity. I need to fix the rotations here for fixed positions before we move into doing more complicated work. Right, so I'll leave this as a comment to deal with later. But by your assessment, then, are you saying that this should just work? Because it only has an X offset? We don't have a bind pose. We don't have a mesh skinned. We don't have any of that. The algorithm doesn't need any of that. We have none of that data. The algorithm is like a straight line vector reposition along that vector kind of algorithm. There is nothing in that case. Unless what you're saying is the functionality has to exist somewhere, and therefore we should look at bind poses to get like a helper function. In your opinion, the algorithm needs that to maintain the initial rotation. Well, I don't think we even need to maintain the initial rotation. The initial rotation is like a red herring here. It does not. The x-axis should be pointing to the next bone in the current implementation. That is what should be happening. Let's see what we got here on skinned mesh inverse bind poses. So mat 4, which we're not working with because we're working with mat 2. I know it's not going to work with skinning later. Let me clarify something. We haven't moved into 3D yet. We are not moving into 3D until I fix the rotation problem for this subset 2D problem. We are going to move into 3D, at which point we would need to care about how to deal with GLTF exports, right? But we're going to make modifications to the algorithm when we do that. I don't really... I get that you think this is important, but it is not the problem I'm trying to work on right now. Right. The fact that it's pointing from X location is fine for right now. Right. The issue here is not that the X is pointing at it. Right. Like you've identified something that we will need to work on in the future. Yes, exactly. The issue right now is that the rotations of each node are incorrect. And they are incorrect in the sense that, like, we have the correct positions of everything, global positions, right? We have all of the correct global positions. If we only use the positions, everything gets put in the right spot. So if we have all the correct positions, we should be able to put everything in the right spot, rotated in the right way, right? Like the third node here should be at the end of this array. At least we identified the cause of your angle confusion already win. Yeah. Also, I'm sure somebody else was confused, so that was probably useful to go through. But the current situation, we have all the information we need. We have all of the global positions. From the global positions, we need to construct a transform hierarchy. The transform hierarchy, right now, I would like all of the transforms to point their forward at the next location. So we have all the locations correct. And the rotations, in this case, I want X to point towards the next thing, right? So really the issue here is that the rotations are putting things in the wrong spot. And it's not that it's not the initial spot. It is the, like it should be the end of this arrow, right? The end of this arrow should have, like, it should look something like this, right? This is a broken clock, so it's probably, you know, right twice a day. So currently, we aren't setting the rotation for the second node. We have 3 joints. We have windows over, we have a windows of 2 over 3 joints. We aren't setting the rotation on the second joint. Here is where I set the rotation outside of the loop for the root entity, right? So inside of the loop, we need to set this entity's rotation, right? And this entity is getting a rotation here. So we could probably just debug this. It's not going to be super useful, I don't think, because there's nothing really to compare it to. I guess let's leave current positions. Debug rotation. So we get the pass through. So we end up with, you know, something going on here. This has a quaternium, which I don't know about you, but I can't read out of a debug log like this. So we can get rid of the root node, which is what I was thinking about doing earlier, right? Get rid of this. So now we have a situation in which the rotation shouldn't be happening for the root or the second node. So everything sticks in place, right? And funnily enough, so it looks like it's inverted a little bit, but so everything is theoretically in the right place, mirrored a little bit, but not moving, right? Because these rotations affect the positions at which these are going to actually exist at, which is my problem. My problem is I have global rotation and global transform, and I'm trying to combine them into being a single unit, and one affects the other, and I'm having trouble connecting the dots on exactly how. Okay. So the question here is, if we were going to set the rotation of the current node, we could do it here, but this requires knowing the rotation, which requires the next node. So I think our logic here has to be reevaluated. We could Windows 3 here and get the next node and just see if it works. We would only get one iteration in this chain, but we do have a longer chain to test. Who knows, it might work. It would fix this Windows stuff. What do you mean by it would fix this Windows stuff? Because I can get the last entity position. Right. So this is going to be last minus this as relative. Last this, where were we? With rotation here. With rotation, quat from axis angle. Vec 3Z. And then this is this dot 2 axis angle or something like that. Two angle. So theoretically, if this fixes the problem, then that's good. Which it definitely does not. So in this case, we need to set the root still outside of the loop. Okay, so that works there. We never get to process the third joint, so it's just in the wrong spot all the time because we never set the transform. That's why it's out there. So this looks correct, other than the fact that we're not touching the last transform. So the question I have for myself is, how do we set these angles? I feel like we set the root out of the loop. I feel like that's a good idea. And then I feel like we need the last one and the next one to do the calculation, which is really awkward. So let's just go with that. Let's go with Chris wrote this horribly, and we're going to, after this loop, I guess deal with the last one. Because now with a chain, with a Windows of 3, we don't get what we need out of it. I think we need to switch this to a while loop with peakable. If we switch it to a while loop with peakable, we can do, I think we get peak back, right? Peak we not get peak back? Next if peak, peak mute, peakable. Iter tools might have this. Peak. Multi-peak. Peaking take while. Multi-peak I don't think is what we want. We can construct the iterator to be the root and then peak peak. And we could mutably operate on the current. Feels weird. Trying to think about how to write this loop. Because it feels like I need to iterate with 3 items, and that feels like I wrote it wrong. But we can do this for sure. We just need to copy the same logic effectively that we did for the root node and do it for the last node. The last node's direction then has to be set by the previous item, right? Or I guess yes. The last node's direction has to be set by the previous items, by its relationship to the previous item. So the rotation of the current is dependent on the previous. Well, let's see. We have this situation, right? Say we're done. Where's a clean image? Say we're done. Say we have like the left one, right? If we go from root to tip, root has a rotation and it has a rotation that needs to be set by looking to the next item, right? The rotation here can only be set by looking to the next item. Let me maybe take some notes here. Root. Rotation can only be set by looking to next item, right? Then we kind of want to carry that value forward, right? So if I'm thinking about this in terms of iteration, we have to have root and root.peak, right? Or like Windows 2 or something like that, right? We have to have something like that. Or we can do index access, we can do, 0, 1, index access, whatever it is. We need to access multiple items. Your guess. In paper graphics, there's 4 nodes, but only 3 bones. The last tip is the tip of the last bone. I think that's incorrect. What is D2? Is D2 the bones? I feel like the wording between joints and bones gets jumbled up. For each joint D1, joint DI, joint position PI. So they're referring to D as a joint and P as a joint position. So in our case, P1 is a transform and D is a bone length. I checked Blender after you mentioned that yesterday, and I couldn't get it to output anything. Not into GLTF. Here's my example. Here's my demo. Since we're talking about it. This never outputs anything other than just a set of transforms that are empty. And I think I can show that because I already exported it. Because I was going to start 3D and then I decided to fix up 2D first. So here's our bone situation in a GLTF export, just to be clear about what kind of data we're going to get, because it keeps coming up, right? We've got skins here, which is an armature, which has inverse bind matrices and 3 joints, right? Joints is not an array. Joints refers back to nodes. So nodes, this is a 3, quote unquote, 3 bone. Where's Blender? Blender's somewhere on this desktop. Let me move this since it's not currently connected. This is 3 bones, right? If we move into edit mode, we can select each of the like nodes themselves. But I'm thinking of this as the same thing as the paper, right? 1, 2, 3, 4 with 3 bones in between. That's what I'm thinking of this as. So this armature has bone 1, bone 2, bone, right? So bone, bone 1, bone 2. So this tip doesn't exist, right? The bones exist. So these all come back into bone and bone length with like nothing on the end. And the data that we get out of that export is like literally nothing, right? Here's bone. Bone doesn't even get a transform, right? And then bone 1 has a TRS, right? And bone 2 has a TRS. But there is nothing else. So we get like transforms at best, as far as I can tell. Go into pose mode, select the last bone, add an IK constraint. Pose mode, last bone, inverse kinematics, constraints. Where's constraints? Constraints. You want an object constraint? Armature child of, none of these are IK. Bone constraint, there we go. Bone constraint, same list. Spline IK, inverse kinematics. I'm assuming you mean inverse kinematics. Bellow. Oh, below. For a second, I thought you meant like a term called bellow. And I was like, what's a bellow restriction? Okay, so we've got IK here. This is on the last bone. We've got a target and a pole target. We haven't implemented pole targets, so we don't have them. This is like in Blender IK. So as far as I'm aware, this doesn't modify the export. Right? This is like setting up physics in Blender. Setting up physics in Blender doesn't export to GLTF. Right? So I export this. We can go back and check. And bone 2 has none of that data on it. There is a use tail option. Include bone's tail as last element in chain, which I assume means this fourth node, which is included in the algorithm. Right. So verbiage wise, I'm not sure what to call these. And in general, they call the bones joints and they call the positions like joint positions or something like that. Blender, I don't think has a name for these things. At least it doesn't show up anywhere in the UI. Maybe there is a name for it. I don't know. But these are bones. I can like the full thing is a bone. Hey, Chris, watch you from Birmingham, UK. Nice. Hope your day is going well over there. Or I guess night. It's probably night over there, yeah? 8 hours? Yeah. It's probably like just after dinner. Which means if activated, the tip of the last bone goes to the target, not the base. Right. Yeah, I understand what you're saying. You're saying that this tip is only included or excluded based on this checkbox when Blender's IK constraints come into play. But what I'm saying in the export is that we don't get any of that, as far as I can tell. We get 0 of that data. We get nothing but bones. And we only get bones at best. Worst case scenario is we get a child that doesn't even have a TRS on it. And the common case is to set the tip. Yeah. I mean, that's what we have currently. I guess I'm not sure exactly what you were, the point that you were making, but that's what we're currently doing. Okay. So we have a way to set the transformations in a seemingly correct way. We just need to access them in a solid order. I think. You think in our implementation of the algorithm we set the base, not the tip? We have a node at the end in our algorithm. So I guess, yes, technically we set the base. But there's no bone length on it, so it's just the tip. And as such, we do not have the tip position to calculate the rotation of the last bone. We do. What do you mean by not? We don't have the tip position to calculate. Let me show you the spawning here. Let me run this. Obviously, we have it like kind of broken right now, but we have 3 joints, 2 bones, right? Every dotted line is a quote unquote bone. Every end point, so the root, the midpoint bone joint thing, and the point the mouse cursor is on, those are 3 joint locations. Because when we spawn this in, what we're spawning in is the IK root, right? And we have some mesh on it. Child is joint 1 with a bone length. Child is joint 2 without a bone length. So this is our tip. No, we don't have 3 bones. We have 2 bones and 3 joint positions. So technically we should add 1 more to align with what the paper does, right? I can do that if y'all think it would be useful. I don't know that it'll help. I think we also have the other demo too, though. So if I comment this out and we do the larger demo has more elements in it. I'm expecting this to also be broken, but That's actually, is that the point you were making? That the last one, why is this working? Xavier, why is this working? Shit. Oh no. So you think that the tip, okay. Okay, so we're just not handling the tip, but everything else is actually working correctly. So maybe I don't do a whole thing here and I just set the last one manually and then I go back and I refactor it later. Because this is like totally working. This is like, yeah, we just never set the tip. Look at that curve. Look at that arcade curve. When did this start working? Did I just spend 45 minutes to an hour like trying to fix something that wasn't actually broken? I don't know. I don't know that I want to watch this stream back. Okay, so in that case, I think what I'm going to do is I'm just going to duplicate the logic. I'm going to suck it up and I'll come back later and I will rewrite this loop. And refactor it because this is just so messy right now. But it is working. So, you know, who's to say whether it's good or not? But that means we need like one more iteration of this. Yeah, if iter peak is none, handle the tip, basically, yeah. Yeah. We don't have a peak on this. Can we get a peak on this? If we peak on a tuple windows, that'll give us a triple, right? Let's debug this. Well, sorry, we can't peekable on this because we're not using it like that currently. We're using it in a for loop. And to be able to peek on it, you need to have control of the iterator. So what I'm going to do for the moment is I am going to do a horrendous move and just say, after this loop, duplicate logic, refactor needed. And we're going to say current positions last and second to last, right? So dot iter, dot next, dot next. Dot rev, let new it equals this. This needs to be mutable. I guess I could Windows this too if I wanted to be a little bit fancier. Right, reverse tuple windows dot next. You do not think so? It will still give us a pair. I think we need a pair, right? I think we need to set the tip based on the position that the previous node is already pointing, right? Because the tip should point in the same direction. So I didn't actually think about how I was going to do this. So if we're reversing, we get last and next to last. Right. So we've got two items here. We've got last and next to last. And this is, I guess I can do the destructuring here too. I'm using regular verbiage rather than penultimate. This is going to be some. Or it's not. What did I do wrong? Oh, else. There's nothing to do here at the end. We've done everything else, so we just have to kind of continue with IK bodies. Current positions, we did into iter up here, so we consumed this. You would set the position to the last position calculated by the solver, but set the rotation to be the same as the bone, the previous node rotation. Okay, so I think we can do that much easier. Set the rotation to be the same as the previous bone. The same as the previous bone. I think we need to still do this whole thing. Because when we're doing this processing, we grab the parent and we grab the current node with the rotation. And really all we're going to do is move some things around here so that we're doing the trying to visualize the rotation of the tip in my head. It's not working. Because if we have this, let's say, and this has already been calculated and it's pointing in this direction, it's got the bone length and whatnot. We already calculated this position. So we have the position, and then we need it to also go in that direction, which will be the vector from 2 to 1. So we should be able to just calculate that. And I don't think we need to keep anything around. So it's going to be, I think, like all of this effectively. And then it's just going to be a little bit of refactoring. This is into iter. Why did I into iter this? Who knows? Who doesn't like a good into iter? So theoretically, we have relative, which is, these are positions. We have next to last position and last position. So we have next to last position, right? Previous no global position. And this is going to be last position minus this, which is the same direction, right? This will end up with the same direction. We get that angle. The previous no global position is the next to the last position. The current node is the last position. With rotation, last position. This is the way that we're supposed to be going. So it's going to be last position minus the previous to do the same calculation. I'm just going to duplicate the calculation right now is what I'm going to do. And then scale and everything gets set. And we get the entity, which is the, who knows, because I didn't merge this, did I? Given that a bonus, same as next to last rotation. Same as next to last rotation. Next to last rotation. We don't have that anywhere, right? Well, yeah, it's the same calculation. This is the same calculation. I'll leave a comment. Same as next to last rotation. And then I need the entity. The entity is easy to get. I'm just going to shovel it for the moment. And I'll refactor later. This has to exist, otherwise something has gone horribly wrong. And then this should be it then. And it is. It works. It works. It's an adventure. I think it took me 7 hours to get to this point total. 7 or 8. Of course, it was all on stream, so I mean... it looks like we're visualizing the normals or something. Okay. I'm going to check my other demo, which is other two things. Well, let me get a short record of this first. What I should really do, what I should really do is not black out the backgrounds for these videos. Dark colors compress really terribly on social media. I really like dark colors, but dark colors compress so very awfully. So let's do like sky 50. It's going to be a bright white blob. And then sorry for anybody that doesn't like bright lights. I really like dark backgrounds and dark videos and stuff. I kind of have a special appreciation for like keeping things low light. But it just doesn't compress well for social media or anything. So if I post this later, it's just going to be terrible looking. You did account for 7 hours a lot. No, you didn't. You didn't account for 7 hours of lost time. I don't even consider the conversation today lost time. I think that was useful to point out that the idea that we would want to keep a potential angle somewhere is useful. We haven't gotten to constraints yet. That's a future topic. We haven't gotten to GLTF yet, or really 3D at all. which is going to be our next step, which is also going to be tough. I don't know. We'll figure it out. But what I want to do is make sure that my other demo also works. So uncomment that, comment this, or handle our out of reach case. We do handle that. Like this. Oh no, you you know what? You weren't here for when I had it actually. This. I just commented it out. We actually are handling it. Now it's in the wrong spot though. No, I broke it. Oh well. We'll fix it. Obviously only one of these has like the meshes on it or whatever, but okay, so what did I do to my out of reach case? I think I need to reset the rotations on everything to be able to do it like this. So transform dot rotation equals quat identity. And we think setting it to the identity quat will clear this out. We also aren't clearing out scale here, so maybe that's an issue in the future. No, I think our handling needs to be a little bit more complicated than that. Right? We get here, then everything sits over there. Okay, so I need to fix this. It worked at one point, I swear. It worked before I implemented rotations is what it did. Because I've implemented rotations, I think that is now an issue. So what we're doing here currently is tuple windows over everything. We get the bone lengths, we get the mouse vector, and we are setting... We're setting all of that, but it needs to include the same calculation we did lower. Okay, so I think I know what to do here. This is going to be replicate code from rotation calculations. But what I want to do there is actually clean that up before I do it. Because the code down there is really messy right now. It's like very, very like tried a bunch of things on stream, figured it out in the end kind of code. So before I replicate it and use it again in another place, I want to clean it up. But in the meantime, we can commit this. And push it up. And I'll do a little bit of formatting here. Maybe I won't. That was really bad. We'll add this, inverse kinematics, format. Examples visibility mesh, cargo fix, P inverse kinematics. Oh, I have a dirty, I guess allow dirty. By just running my fix commands and stuff. Cool. Push that all up. I wonder what changes that made. Oh, this isn't even in a pull request. This needs to be in a pull request. I guess I will upload some stuff. Screenshots from today. Cool. There was a comment. Maybe just getting the code that applies to calculated global as local rotation, so it needs to be taken out of the if block. Can't really see all the braces to evaluate that. Yes, I understand that. That is, I think this needs to be a different loop. In my head, there's a reason that this looks so weird, and it's because I am doing loops in the wrong way, calculating maybe the wrong things. I think this should be a peekable iterator at least, and then we should manually iterate over it with while, which will clean up this whole thing because then we can peek forward. And we can even peek mutably, which is really cool. So we could do like we could do a double peek forward, and if there is only two elements, maybe switch out to a different processing, like that kind of thing. Oh, you mean for the out of reach? If out of reach, do our stuff, else do the solver loop, apply the transforms. You think you want to see more functions? I think maybe. So we've got this like general update function, right? We do the, if there's no mouse, then we don't do anything. Otherwise, we loop over this. We could do, this is just calculating the total length, calculating the translation of the root element. I actually did fix that, so we'll remove that comment. So in this case, we basically do like if total length, yada, yada. We need the mouse vector and access to some of the queries to get some of the data to do some of the stuff. Just reorganizing the if break would not require duplicating the apply transform, but more functions would also clean stuff. Yeah, it depends. I think there needs to be code cleanup. It doesn't necessarily need to be up here. Up here is pretty clean, straightforward. I think maybe if you're not used to seeing iterators written like this, and maybe I use different terminology here instead of P2 and P1 and IT. These probably are too short for somebody to really understand what they are at a glance. But like this is a single while loop over those elements. This is setting the first position. This is a single while loop. And then we diff. So this loop here is pretty well organized. We could break this out into a separate function here. So like shrug, maybe, I don't know. Would have to play with it a little bit, see if it makes sense. The only thing that I have a concern about with breaking stuff out in examples like this is the person reading us for the first time will have to jump around the code. And jumping around the code is not very conducive to being able to like learn things. It's harder to jump between 3 or 4 functions than it is to just read a linear section of code. And we aren't doing very much mutation here, so it's very much like the only reason that things are mutable in these senses are to mutate that children array. A couple of things we didn't actually need here, these bone lengths. This whole section here probably needs to get rewritten. I want to basically rewrite the loop so that this section is unnecessary. That's what I want to do. I want to have a little if condition at the end that says if peekable is none or if peek is none, then also set the transform on the tail. Replacing a big block of code by just a solve function does sometimes make things easier to understand. I think that can be absolutely be true. I don't know that it's true in this situation, but it can absolutely be true. I think that in the majority of cases, when I see like 3 high-level functions or 4 or 5 high-level functions, it's not necessarily easier to understand per se, unless there's also been thought put into why are those the functions, like what are they doing, like etc. But in any case, relatively happy with this. Definitely going to refactor it. Definitely want to do 3D. You would put the whole forward backward passes into a solve function, but not important. Yeah, I would call it like forward backward or something like that. But yeah, TBD. There will be refactoring is basically all I have to say about that topic at the moment. I think that the whole situation here needs like a once over. Okay, I'll push that up and then the question becomes, we have 2 options here. One of them is we can go straight to 3D. The other is we can like, skinning is the wrong word for this, but is it 3D now? Maybe I'm missing something. Why don't you go with an abstraction like in the Plurio example? Just because I wanted to keep things a little bit simpler to start with. That's it. I did 2D first because I know 2D is simpler. It has fewer variables. I can get the angle directly in 2D, right? I can take a vector, subtract it from a vector, get the angle. In 3D, you kind of have to do like a dot product or something. So this is like step 1 on a path, if that makes sense. Like going straight to the end is the thing that I didn't do. To be pedantic, the forward backward passes are not the full solver function. Solver function is that, but with the loop and disk tolerance exit condition. Yes, agreed. Yeah, so I basically just like, this was my first time seeing FABRIK, taking it for a spin on a scenario that I know is simpler overall, right? Debugging spinning vectors in 3D is not as simple as debugging a spinning vector in 2D. But yeah, I mean, the goal is to take it to 3D. So we've got update in here. And all I'm going to do is delete that whole function and drop in code we just wrote for 2D. And this is not going to work. Is that the blues sound? I think that was. Startup, spawn, bone, joint. So we kind of have a similar setup where we have like some kind of root IK node, and we have a set of joints. I am going to need some kind of target. So we're going to have to add an actual target and not use the mouse here. We'll do, I don't know, like a sphere. So yeah, to finish off the like, why don't I use an abstraction? Well, because the abstraction comes after I understand what actually needs to be abstracted. And before this, I did not understand what would need to be abstracted. I was just kind of going through the algorithm, implementing it for the first time, not really understanding. Before going to 3D, fix the out of reach case, fix the iter descendants that will not work in real world use case, send the end effector to oblivion. The end effector is already gone. We could fix the out of reach case. It doesn't really feel like that's blocking us from doing 3D though. You know? Fix the iter descendant that will not work in real world use case. We can't really fix it without having the problem. So I guess like we could stay with 2D for the moment. And do, let me finish my thought over here first. Oh, come on. That's why I always go to the other example. Throw in a circular base for funsies. These need to be very different sizes because they are no longer... also, the threshold is going to have to be different, I think. Let's make these like... I guess 3 and 5 and 2, I don't know. Cube light, let's drop a light in here. Let's use the camera from this scene example, why not? Yeah. And then I want a sphere here, and that's going to take a mesh material 3D. And a transform. They put their cube here. I think our cube is going to be controlled by a system, or our sphere is going to be controlled by a system. So, yeah. You totally agree with you. Trying it out and understanding how basic IK works is a good idea, but moving forward, trying different algorithms, FABRIK, CCD, 2D, 3D, and then using a small abstraction is great. Cool. We'll keep that in mind. We can fix the iter descendant issue by setting the bone with the IK constraint as the last bone, not the first, with a member that sets the IK chain length and then iterate backward. By setting the bone with the IK constraint as the last bone, not the first, with a member that sets the IK chain length and then iterate backward. Yeah, but we don't have any of that data in GLTF either. Right? So if we're going to do something like that, we can design components, like the current component would work. We can design components, go from bottom to top. I think the the paper actually goes from bottom, top, whatever we're going to call these things, from end effector to root. The paper wants to go in that direction to find all the bones. I don't particularly think that would be terrible as a refactor. The only place that I can remember that we use that information is to construct the original positions of the bones. So that current positions array. Right, current positions needs to get built from something. And then in current positions, we can also stick, the entities or whatever. And this is really the only place that we care about iter descendants in that sense. So the rewriting wouldn't be that bad. Like none of the logic would need to get rewritten, I don't think. Right? Just looking through this and where it's being used and stuff. Right, and then when we apply the transforms, we iter again. But if we store the entities here, we don't need to iter. Not like this anyway. So that would actually simplify this area. And then yeah, so you're saying that you would want let's make sure that I didn't change anything in 2D. Okay. So we can do this. Instead of inverse kinematics, we want end effector, bringing back the end effector component that you don't want. We can iter ancestors. It doesn't matter. We only need to call it once. So we only need to do it and then accumulate and then reverse. Inverse kinematic end effector. It feels weird if you're constructing it in code to put this on the end. I know that makes it easy programmatically, but it does feel a little weird. Okay, so let's do this. Let's do inverse kinematic end effector. And then we can also I guess we can set the number of bones. Setting the number of bones feels like something that isn't useful. Like if you're setting this in Blender, right? If you're putting a component on something, do you really want to set the end and then count the bones? Not really. I guess you could select all the bones and easily insert a component or whatever. I don't know. This just doesn't feel particularly like an improvement. And like, if this is number of bones, then are we counting bones or are we counting joints? Right? Because joints are the transforms for us. In this way, it would bring back the end effector, but I mean, also make the inverse kinematic root disappear. Yep. Number of bones is useful to iterate to the root if the root does not have a component anymore. Yep. Unfortunately, that means that you need, like, the trade-off there is, do I count the bones or do I put a start and an end, right? And I think one of those actually makes it easier to do in Blender. So like if we have inverse kinematics, which gives us all the roots, and we have inverse kinematic end effector, which gives us all of the end effectors, right? Then we can go from end effector to root, and it doesn't matter how many bones there are, right? Like if you're doing a tail on a dragon or something and you wanted it to be arcade, counting the bones sucks as an experience. Putting a component on the tail and a component on the base of the tail feels better. Right? All I'm saying is that it doesn't feel great in any way. I think coming up with a better API might be better. I think 2 components is what I'm going to go with for now. I can't see any reason to like have the bone amount data before we calculate the chain. Like that just doesn't feel like something that is particularly necessary. I guess it could make for a good or an interesting like demo, right? If we have the end, but then like you could just replace the component and it would do the same thing. So I don't know. It's I think limiting the iteration when going from tip to the root is easier than forcing the user to set the right components to the right entities. You think people can't identify the root bone that they want to put it on? I think counting results in like, which thing am I counting? Am I counting the knobs or am I counting the bones? Especially from like GLTF or something. And then like, for example, if I was writing this, right, here's my stuff. This is going to be an inverse kinematics root. So this would be the inverse kinematic end effector, right? And then even here, I would need to go back and go, okay, is this 1 or is this 0? This is 0, so this is 1, and then this is 2. Or is this like 1, 2, 3? I just don't see how setting the number of bones is easier, personally. Inverse kinematic end effector, right? And then you only put it on the tip. And then you tell it to go backwards something. And then you get rid of this. So now from here, you have to count backwards some number and figure out what that number is. How do you figure out what that number is without being like, is that the number of children? Is that the number of nodes? Is that right? Like how does somebody who doesn't know what they're doing, so to speak, figure out what number this is? Because for us, we know this is the tip, right? And if you said technically like tip with 1 bone, I think it's tip and joint 1. Tip with 2 bones would include IK root. So this would be end effector. Affected bone count 2, right? I don't know. Maybe other people feel like this is also more intuitive. It's fine in any case. It doesn't really matter either way. If we were turning this into like an IK library, I would care more about the API design. For now, we're just trying to solve the iter descendants issue. But now, yeah, now I need to like go through and count. Like this is now a process, right? So like affected bone count. So I'm an affected bone, 1 bone, 2 bones, right? And then it'll also be true for this. So that'll get rid. And then how many bones is this, right? Bring in joint position here, right? Like how many bones is this? And now it's like, okay, so we're here. I guess we go up to 1 bone, 2, 3, 4, 5, 6 bones, right? And this is if there's like a single chain. Yeah, you just said 7, right? That's my point, right? So inverse kinematic end effector, affected bone count. Right, but that's my point. My point is like, how do you figure out what that number is? And that number can have multiple interpretations. So like the way we currently have it set up would be, this is the 0th bone or like the joint effectively, right? So saying there's 1 bone would bring us here, 2 bones, 3 bones, 4 bones, 5 bones, 6 bones, which would be 7 joints. We're going to roll with it for now. But I don't actually think this is a good user experience. I think that solves our problem, which is all I'm looking for at the moment, but I don't think it doesn't really make sense. I don't think. If that's how everybody else does it and people are used to that, then cool. But like, it still feels weird. Okay, so we can't query for IK roots anymore. We have no idea what the roots are. The only thing we can query for is the end effectors. Right? Inverse kinematic end effector, and I guess we need entity now and this. So IK end effectors. And then IK end effectors. This is trying to iterate over each IK body, which I think is fine. I think IK end effectors is good for this, right? We have all of the end effectors with the data. And this says root entity, root bone length, which we use quite often. But I think we mostly use that for iter descendants related reasons. It complicates the code in your example, but more similar to other apps, more in line with the data GLTF would give, but this is also customizable. Yeah, I think there's a better solution somewhere, but I don't need to find it right now either. So root entity, root bone length are not things we have anymore. We have end effector, entity, and end effector. What did we call this whole thing? We called it inverse kinematic end effector. So we'll just call it end effector. So total length then is the end effector won't have a length. So this goes away. At least in our current implementation, it doesn't have a length. So maybe I leave like if end effector has length, add it here. But if end effector has length, then it's not the tip. So then we need to do, do we have parents here? We don't have parents here. We need parents, query, child of, right? And then this is parents dot iter ancestors, end effector entity dot take end effector affected bone count, right? Because we have hours and we need all of the rest. And then we filter map over bone lengths, map them to bone.0, sum them. So this is still the total length. +1 maybe. Why would we +1? The end effector length is 0. So global transforms get root entity. This is drawing a circle over that last entity. So if we wanted to do that still, we would have to iter ancestors we do grab the root entity quite a bit. So maybe I put let root entity equals this, and this is nth. Right, so now this is if no root entity, continue to another body. Which means that we can then keep this and this global transforms, get the root translation. Total length is the root translation minus the mouse position. Then we do this stuff that we haven't written yet. Current positions is the root translation with the root bone length. So we don't have anything here yet. Given we take nodes and affected bone count is the bone count, not the node count. Oh, you mean take +1? The bone count lines up with the amount that we need to take, I think. Because if we take 4, we get 0, 1, 2, 3, 4, or 0, 1, 2, 3, right? So we get 4 items. And that would mean root node plus 4 items. So we would have 5 joints, 4 bones. So in our case, we will have the root entity, which is the tip taken out. 2 bones is those 2 entities. So I think take the number is the right solution there. Yes, if the IK chain length is 3 bones, we need 4 nodes. If you include the root, which we just skipped. Right? Iter ancestors on this entity. This is our 4th entity. This is the other 3. Current positions. We need the current positions to get built. We need to get built in this case, the reverse way. So we basically parents iter ancestors take chain the current node, right? So this is a tail chain for us, right? No, we have to reverse. So this is going to be the same thing. It's just not going to be root and root bone length. This is going to be the transform that we get from the other stuff. You forgot iter ancestors, iter descendants does not iterate the first. I was literally just talking to Jan about that in chat the other day, yesterday actually, and I was like, "Dang, doing this IK stuff made me really wish there was like an iter descendants with self. You know, that would have been really nice. Iter descendants with self, because then we wouldn't have to juggle this stuff like this." So I might make a PR for that if I can find the time. I got to catch up on This Week in Bevy today. So I don't know that I'll have the time, but TBD. So total length, circle 2D, root translation. We need, or we have the end effector entity. So we can grab that and we can grab the global transform from it. I guess we could include global transform up here since we never mutate it. And then bone lengths could also have its global transform, which might make this a little bit easier to code. Right, we can't mutate this anyway, so this is bone lengths.get.ok map bone.0.0, which just looks a little weird, but it's fine. And then this is going to be the end effector global transform and a bone length of 0. And we're going to chain that with parents dot iter ancestors take which we can then map over, I think. This is bone lengths.get, so we can do bone lengths.get and do our translation.xy here. Which is also what I want to do here. .get, .unwrap, .get, .map. Bone global. Transform, so it's global. .translation.xy, bone. Right? Unwrap. I don't want to filter map this because I don't want to like get things lost. It's the wrong place to put that unwrap. Maybe a rev is missing. A rev is missing. Not yet though. Rev is going to go down here. But that might not be the thing that we are able to do. But I have a different issue first. Dereference this. I guess this doesn't have a thing, so we're cloning here now. That got uglier. Chain. Is there an iter tools reverse? I think the issue with reverse is that we're going to have to collect anyway, and then we're going to have to reverse because we can't reverse on an iterator that doesn't have double-ended. So this will collect, and then current positions dot reverse, which is a mutating thing. So end effector distance, iterations, yada yada, everything's set up here correctly. There are no other issues, as far as I can tell. Does it work? No root. No root. Is it not nth? Is this supposed to be -1? Because it's 0. It's kind of annoying, but so that works. And now we've effectively gotten rid of the issue. So let's make sure we've gotten rid of the issue and go for mesh 2D. And this is going to be a child now of ik root. And this can be with a rotation at some point, but let's just start with having it as an extra child. So this shouldn't matter because we made the refactor. Everything should still work. Which it doesn't. So what's the problem? This is a child. There's a joint. Do we iter descendants anywhere? We do. We're iterating descendants on children. I think we don't need children. So let me get rid of children, at least temporarily, to kind of highlight the areas that need to be reversed. In this case, I think I'm just going to comment this out because we didn't implement that logic anyway. End effector, we already have. This is end effector. Global transform dot translation dot xy. So we don't need to do that anymore. And then children, iter, descendants for this loop that we're doing. I think the thing that we said we were going to do here is that we're going to include the entities in these queries. So we do children built up where current positions, right? This is going to be a vec of stuff. In this case, it's a vec of bones and global. So bone needs to have the entity. Maybe just iterating ancestors just once and storing the entities in an array would make things simpler to iterate over later in both directions. That's what I'm doing. Where is my bone query? Bone lengths. Entity. Right? And then anywhere we need bone lengths is going to do this kind of thing. This is going to have entity in it. And we're going to include entity here, which is going to be an issue because we don't have it here. And then this, I don't think we care about the entity here. Don't care about the entity here either. And then these have additional destructures. Entity P1 and entity P2. I guess we don't use them. So those don't even need them. And then this doesn't need to be zipped, right? Because the only reason this was being zipped was to get access to those entities. So this gets replaced. And the root entity changes to be the third slot, which is no longer nested in that. And then here we get, this is after the loop right now. This is in the loop. So what we're ending up getting here is dereference. Do we need the entity here? Let some. We do need the entity somewhere. We need it here. This entity is the end effector entity. So we don't even need to care. We just know it's the end. And we run. And this looks like it works. Which is great because now we can go back up to the mesh 2D. And we can change this transform to be dot with rotation. What is this? Quat from axis angle vec3 z pi. Frac pi 2? Frac pi 2. Right, which sticks this hopefully on the right angle or on the right line, right? So now that's there. And really the from XYZ is, what is this height? Over 2, 0, 0. And now we've got our mesh controlled by our IK. And we do effectively the same thing down here. We have this mesh 2D section, and it needs to go into children now. And this needs to use the same distance calculation. And now we're really cooking with gas. Now we've got IK on with our skinned meshes or whatever, instead of just gizmos. And then we can probably do the same thing for all of the other bones in the other example, which is going to get horrendous. I'm going to be honest. The level to which this is going to explode in size is pretty big. So in this case, we've got children with the bone lengths and stuff, and we're just going to collapse this down a little bit more, I think. First of all, it doesn't need to have this, and it doesn't need to have this. But what I might do is, because these are all the same, we're just using length for everything here. Right, that's right. Group position, translation distance. I think we're just going to hard code that. And then materials, same kind of thing. We're just going to like shove this up here, do some manual formatting. Root position, joint position aren't in scope. Let's uncomment that section. And then we need this distance, right? Over 2. And I'll inset this, and hopefully this is going to be a little bit more readable. Oh, you did not see that, but yesterday spurious change of rotation disappeared. Spurious change of rotation. Oh yeah, you mean once we started doing the oh, sick. What was that? Let's comment all that out. The spurious change of rotation, I think, was related to not handling the rotations correctly. But yeah, we'll see. This needs to be dot whatever, comma. What is the issue here? Meshes and materials aren't in scope? No. All right, bundle has duplicate components, debug name, transform. Joint position. Because this is not supposed to be this, it's supposed to be this. Right? It's supposed to be just an extra child here, not a... So that's the correct thing. Unfortunately, this is the new start of every single children. So mesh whatever, here's name whatever, mesh whatever, these go indented to meet those, these go indented to meet those, these go indented to meet those. This is just a horrendous test setup is really what this is. And Rust Analyzer, or Rust format, I should say, wreaks havoc on that passage. So here's all of our meshes set up correctly as children alongside the joints because we've now set this up appropriately, which is super exciting. Unfortunately, I don't think we make it to 3D today. But fixing the problems in 2D is worth it. See how when there's no mouse, it starts out like that? They're all kind of just there, facing a direction or whatever. Maybe there's a better way to like enable bone setup or whatever, but my mouse hasn't moved yet, so it still looks like that. And then immediately snaps to where it's supposed to be. The algorithm is snapping it there too. It's not anything in particular. That is relative to us not keeping the original rotation. Yeah, but I don't think, do we ever want the original rotation? I guess, maybe. Because like the point is to find, ooh, inherited visibility. What is going on there? Hang on. Entity 18 with the inherited visibility component has a parent without it. So that just means I messed up my mega thing here. We'll need the original rotation later for proper skinning. Yeah, maybe. We need to have that problem first, though. What is going on here? Entity 18, 19, 20, 21. So it's all of them. Has a parent without. So children is on name and joint position. So for all of these joints, we need to have the inherited visibility stuff on it. Do we still have a spatial pack? I think we just need to do visibility, right? I think it's visible. Visible. Let's find out. Docs. Visibility. I guess inherited is the right thing here. So for all bone lengths, go below the bone length and insert a visibility. It's weird though, right? Transform, I guess transform doesn't include visibility. I guess that makes sense. So now our warnings are gone. Same rotating as the starting situation, but why would you want the rotation on the starting situation? Right? Why would you want that? In this case, we definitely don't, but maybe in the 3D case, it's more applicable, but I guess technically you could put something on this in any direction, but cool. Let me take a little shot of this. Cool. Well, the user set, quote unquote, the user set the blue rectangle to not be pointing in the same direction as the bone. You'd expect this relative rotation between the bone and the box to be kept same all the time. If we don't do the rotation, then it doesn't work correctly, right? Right? Like if you're saying the user set the rotation is always relative to the direction it's facing. So it is being kept. The rotation is being kept. I guess what you're thinking of is like if somebody wanted a static rotation compared to the actual bone, like something that was disconnected from the bone. But like if we set a rotation, the rotation sticks. The rotation is just relative to the bone, right? But in any case, I'm pretty happy with that for the day. It's getting to be, I think, yeah, almost 12. So I'm going to call it for the day. Next stream will probably be Monday. Thanks everyone for hanging out, and I will catch you in the next one. Later.